come up with a linear form of it, right? Why have we required a linear form of our equation? Because remember, like if we're starting, even if we're starting with a polynomial, what we have is like y equals ax squared plus bx plus c. We've turned this into a linear form each time, right? What we've said is we're going to do variable substitution and say x1 equals x squared, x squared, x2 is just equal to x. And so then this becomes y equals a x1 plus b x2 plus c. So it's linear with respect to x1 and linear with respect to x2. Or if we did it with exponentials, or if we had like y equals a times the exponential of bx, we've done the natural log and said natural log of y equals natural log of a plus bx. So then we have, this is our y term, this is our x term, that's our slope. We've done this. Every time we've converted it to some sort of line or combination of lines, like there. Why have we been doing that? What's that? Yeah, we need to have that relationship. It's required for our regression. Excel is assuming there's a linear relationship in your variables when it does a regression. It doesn't know any better. And so you have to give it something that Excel can do in a linear form. Well, do you think you can linearize every equation? No. I will tell you, 100% you can. You can come up with forms, like polynomial ones are easy, logarithmic ones are easy, exponential ones are easy. And they're generally relatively straightforward to do until you get something like this. For instance, y equals ax1, x2. For instance, how do I linearize that? I really can't, right? Those are stuck together. There's just no way around it. Or if I have y equals ax1 plus ax1 squared plus bx2. This one you can do a little bit because I can call my new variable this one, so that was not bad. This is where it really falls apart. Let's introduce logarithmic functions, or trigonometric functions. It's basically impossible to linearize those. You can do some sort of like, not Fourier transforms, Gaussian sequences, I think is what it is, where you can create approximations of what sine is and approximations of what cosine or tangent. The problem you run into is they're not really accurate and they're big, ugly equations. So what do you do when you can't linearize it? Any ideas? Any random guesses? I will accept both. Why is this so slow?
Your computers are still on screen ready.
So what we're going to do is we're going to go over an example today of one that can't be decoupled. And here's the thing, even an example we've gone over so far is easy. Like we've said, oh, you can decouple it this way, but what about when you can't? And let me show you that example, because this is the one you're going to do. So we're going to do an example in class, and that's going to lead into a homework that will be due Wednesday before class, and then I'll go over the solution in class. So let's say we have some sort of we don't know A plus some amount of B goes to C, and we don't know what the coefficients are. And let's say it's a polymerization reaction. It's a block of polymerization reaction, which is why we don't know what those values are. But that gives us some form of the reaction equation. Looks like R equals K, concentration of A, concentration of B, and we've got this raised to the, I'm going to say C, no, let's not use A and B because let's use M and M. And the reason I do this, I want to keep my coefficients in terms of A, B, C. So this is concentration of N, this is concentration of N, raised to the A, raised to the B. This looks relatively easy. But what's ordinarily in your reactor, what's happening is you have this reaction going on and you're varying, what are you varying on your reactor to change the reaction chemistry? What's that? You're often changing temperature. Have we introduced temperature in here at all? Where does temperature show up? And we haven't discussed that. Y'all remember the equation that defines that?
Radius.
Yep. Arrhenius, A equals, K equals A e to the negative EA over RT. And we have A, which is a variable, or is a constant for this system. We have our activation energy, which is a constant for the system. And so now we have to plug these in, and we get R equals AE to the negative EA over RT times M raised to the A power times N raised to the D power. So you're only controlling the concentration of M and N, or they're coming in from somewhere that they're defined, and you're controlling the temperature, and you're letting everything else happen. This gets to be non-trivial now. I cannot linearize this easily, as you can imagine. This becomes very, very challenging to do. So, what do we do with this? Well, if this ever catches up with itself, I'll show you. Okay. And I'm going to post this data on Blackboard, so you'll have it. When Blackboard comes out. It opens everything for some godforsaken reason, I don't know why. And the question is, how are we going to do any of this? Well, because we still need to regress it, right? We still need to figure out our values. And so what we're going to do is we're going to do this in a way that hopefully will make sense to y'all, and you'll be able to figure this out relatively easily. This is not what I want. Kill this. So we're going to go over two examples. We're going to do a simple form version, and then we're going to do a more complex version. And then I'll leave a version for y'all to do and submit in homework. And I'll make it active. I'll set up a homework submission portal after class. Today's the 17th. Now, the challenge when we're dealing with data like this is, you'll have this in just a second, I apologize, is that we have to know what we believe our equation form looks like. Because here, you can't guess every possible nonlinear equation. Like, you will lose your sanity trying to do it. So you have to come up with guesses that make sense based on the data you're looking at, and just hope it's, you know, in a sense, hope it's right. So we're gonna work with data that is clean, and we're gonna do that because this is, I wanna make sure that you get the material, instead of dealing with overly complex data, it can be a real pain. So we're gonna start with, like I said, some very simple forms of equations, and then we're gonna deal with some more complex ones, just so you guys can get a feeling for what to expect. We'll get through as many examples as we can today, and then it'll leave at least one for you to work as your homework. We're just gonna work our way up in complexity, so let me save this, post this on Blackboard, and you guys will have access to it. Okay, it should be visible to you now. Let me know if you can see it okay.
Are you okay to show it on the screen?
What's that?
Are you gonna show it on the screen?
Oh, I don't have it. I'm gonna put it up there in a second. But you should have the data available on Blackboard now, or you can download it. Okay, cool. So we're gonna start with, so sheet number 3 is the one you're gonna do for your homework. We're gonna start on sheet 1 and kind of work our way through simplified models. So what we're dealing with here is trying to decide what is the model we think we should look at. And so I've given you on each one what they are. I told you this one's exponential. This one is a weird sine structure here. This one is even worse. Exponentials and sines in there, just to show you it'll work on more complex. And this one is going to be basically that kinetics problem. And you're gonna have to solve it based on this data. And here, you're given what you'd like to be given. Your rate of reaction, you're gonna be giving your concentration of your two components, and your temperature in your reactor. the things that you're realistically gonna know, and trying to calculate what your kinetic parameters look like. And you're gonna have probably some noisy mixture of data, not just clean data where you have one. Ideally, what you have is one of the values is constant, everything else is changing, or let me say it, like you have one where C and D are not changing, your temperature is, so you can just regress temperature by itself. Or D and temperature are not changing and C is, so you can regress C by itself. You can do each one individually. That would be the goal. Reality, you may not have that. In raw process data, you're gonna have a mixture. So we're gonna learn how to handle when you're dealing with that. So, you're given this, and let's plot what these look like. The population versus, population of cells versus basic growth time in hours. So first thing you're gonna do, I've told you what the model is, but if you don't know what the model is, you're gonna plot it. That's gonna be your first trick. You're gonna, okay, I look at this, and what I see is something that looks like this. Hopefully, when you hear cell population growth, and you see that shape, your instinct is exponential. It doesn't necessarily mean it will be automatically, but hopefully your instinct says, this is probably exponential then. So, we're gonna now work on what is the equation now. What's nice about this one is we have all of our data. So if you couldn't linearize this, or let's say if you were, let's say you didn't linearize it, you had data that was already linear, what would you do to regress the model? To figure out your equation? Yeah, if this was linear data, like the way you'd expect it to be, how would you regress it? Like how would you get your regression coefficients? So if you knew this was like y equals mx plus b, what would you do?
If you knew it was linear?
Yeah. Right, you would just basically tell it regress it, give me the parameters, right? You can do the same thing. Here's the problem, is when it's nonlinear, you just have to do it manually. But it's doable, it's completely doable. So let's walk through how you do this. I'm gonna pull this down so I can, because I'm gonna put in some data up here. What I need to come up with, why is this, I need to, this screen is terrible, just the brightness on the screen. I don't know how I'm gonna mess with it. Okay, so, right now you've got your X and your Y. Well, we know we're gonna need a Y predicted, because we're gonna be developing a model. And I'm just gonna actually put it down here, I'm not gonna, it doesn't matter what you use, like where we put it. And I'm going to come up with what my model looks like. Looking at this, I said, it's exponential. I'm pretty confident it's exponential, so I'm gonna use an exponential term. And I'm gonna use this equation right here. Y equals A exponential B X plus C. So the plus C term is, could be internal, could be in the exponential, it's not clear here. Let's assume the C is in the exponential, just for the sake of argument. Or actually, we could even do this. We could do A times the exponential of bx plus c. Oops. And then we've got plus d, another constant term just hanging out there. And it won't hurt anything, like we'll regress it with all that. So that means I'm going to have to figure out what my values of A, B, C, and D are, right? I'm just doing this so I can, I'm doing this for bookkeeping, and I recommend this because this works pretty well. And then we're gonna figure out predicted value for that. Because we don't know what it is, right? So it's gonna be predicted A, predicted B, predicted C, predicted D. And now let's just put values in, arbitrary placeholders. I put 1 just because I can just hit the same button every single time. It doesn't matter what value you put in for placeholders, just put a placeholder value in. The reason it's important to put a placeholder value in is when you're doing your analysis of this and your regression, it's gonna need a seed value to try to solve it. If you choose 0, that will often cause it to choke. I don't know why, it just does. So if we give it a positive value of 1, it generally will be better. Now we're gonna create our predicted Y. How do we make our predicted Y? Well, we have an equation, right? And we have what values we're gonna start with. So we just build it. we just build our predicted value. We say y equals, so a, so, and I'm gonna lock that because I don't want it to move, times the exponential of b, lock it, times x plus c, lock it. And then I'm going to add my d term here and lock it. So all I've done is recreate this equation here. I said a times the exponential of bx plus c, and then plus d. I'm recreating this equation using the constants here and the x value. Does that make sense? Because what we're going to do is we're actually going to regress these constants to make this prediction match the actual value. But we're going to do it manually. So it's going to look the same. Mathematically, it's going to be the same. You just have to do the work manually to make it, because it's no longer linear. And Excel expects it to be linear. So I do that. I'm going to drag this down. The shape looks right. Like if I plot this, actually, no, don't want to do it that way. I want to put it in here. Chart design, select data. So I'm going to edit this one to be y actual, the one that was already in there. And I'm going to add a y predicted. My x is this. My y is this. Okay. It's curving the right direction, so it makes me go, okay, our model's probably good. We just don't have the parameters right. Now, when we're regressing a model in Excel, how do we determine whether it's a good fit or not? What are the things we look at? R squared and residual, right? Those are the things we're looking at. R squared tells us whether it thinks it's predicting well, and the residual tells us whether we think the model is the right model or not. So those are the two things we're going to look at here, too. We're going to do residual and R squared. Okay, what's residual? What is the actual residual represent? Y'all remember?
Distance between your expected.
Yeah, it's the difference between your actual y value and your predicted y value by your model. So, I just do y minus y predicted for each one of these. Now I have my residuals. Does this make sense?
How did you do that? Sorry.
Oh, it's just y minus y predicted for each data point. And it gives us our residuals, and we have those. Now, you're gonna need to get R squared. This is where it's a little more challenging. Because what we wanna do is, I'm gonna put up here, we've talked around the concept of R squared and what it is, but we haven't really talked about exactly what it is. R squared is a measure of your residual, but it's a normalized measure of how your residual is. And it's governed by the equation 1 minus RSS over TSS. RSS is residual sum squared. SQUARED. And TSS is total sum squared. Now, this one, RSS, is exactly what you think it is. It's yi minus y predicted squared, add them all up. Why are we squaring it? It's actually done for simplicity reasons. If I have residuals that are alternating negative and positive, if I don't square them, and I add them together, I can get a value that's 0 when the residuals are terrible. Because I can have one that's off by plus 100, one that's off minus 100, they cancel each other out. When I square them, I eliminate that, and I make the residuals now more powerful. Because if I say 100 and I square it, I go to 10,000, minus 100 squares goes to 10,000 also, now it's 20,000, it looks further off. And that's what we want. We want it to be like, oh, you're way off, I need to fix you. If we don't square it, we run into that problem. So this is your RSS, residual sum squared. TSS is actually yi minus y bar, or the mean value, squared so this is saying, okay, this tells me how far my model's off. This tells me how much spread I have in my data compared to my mean. So how is my model behaving compared to my mean? If all your values are close to the mean, then that number gets very small. If you have a large span in your data, your TSS gets larger, and it says, hey, I expect this RSS to have some amount of like deviation because this occurs. This is compensating for the amount of deviation that occurs and normalizes it. Expected deviation versus model deviation. Because otherwise what can happen is your residual will struggle to predict properly. And so it's a way to normalize your residual. And so you can imagine if your residuals all go to 0, your sum of the squared of the residuals goes to 0, 1 minus 0 over some number is 1 minus 0, so 1, your R squared goes to 1. That's a fantastic R squared. As RSS gets bigger, TSS does not change because this does not depend on your model. This is actual data minus mean of actual data. That means that as RSS goes up, this piece goes up, your R squared goes down. And eventually the most it should be off by is this. But in theory, you can actually go negative. It just doesn't happen very often. So we're going to do this analysis right here for R squared. So first thing we have is our residuals. Second one, the second thing I want to do is I want to do my residual squared because I don't want to have to add it up in one equation. So I do it table-wise, so I calculate it for each one. So I'm going to do residual squared on each one of these. Then I'm going to need my RSS term up here. And that is just the sum of my squared residuals. Now I need my TSS term. We have to calculate my TSS. And I'm going to do it piecewise like I did my RSS because it makes me feel better to do it that way. So I'm going to do yi minus y bar, or mean, which means I need the mean of my y's. So I'm going to put in space for the mean of my y's also because I forgot to do that. And move these down. So my mean y value is just equal to, literally, the average of my actual y's. Why does it supposed to do that? So we just get a value for it. And then I'm going to do yi minus y bar. So y minus, and that we're going to lock because we want it to always subtract the same mean every time. By the way, stop me on a step if you're confused. Because I want to make sure you're keeping up with this. What's that?
I'm just trying to keep up.
Okay. If you want me to slow down, tell me. I can definitely slow down a little. Everybody at this point where you did the yi minus y bar?
Which one's yi? Is that the?
Y is just your
or
actual y
Okay.
value, your population. Yeah. Yep. Anything done with TSS is only addressing actual data. It's basically, that's how it compares your residual or your model information. That's what it's comparing it to. So TSS is just looking at actual data, yi minus y bar.
And then y sub p is, the predicted.
Yeah, y sub p on the RSS equation is predicted. So we're going to be doing that in a second. So now that I have the yi minus y bar, I need to square it for my TSS. So I'm gonna go ahead and square those. So that I have them, and I don't have to deal with it. And now I'm just gonna sum those up for my TSS. I'll put yi minus y r squared. That way you can remember what each of these is. So now we should have everything we need to get our R squared value. We insert one more blank line so that I have space in my data. God, this now sucks.
TSS is the sum of the y minus y bar squared.
Yeah, yi minus y bar, yeah, and TSS is, then you square those and sum them up, yeah. And again, same reason we squared for RSS is why we're squaring here. Is to get rid of any negative signs and to bring everything to a positive difference from our mean. And also that allows us to do direct comparison between RSS and TSS because they're the same units. You could do absolute value, it's less sensitive to error. And it also doesn't have a statistically defined term, so you can make up your own, basically, fit equation at that point. But it would be far less sensitive to error. And so now we're just gonna do R squared. And our R squared is just 1 minus RSS over TSS. 1 minus, I'm gonna put it in parentheses so that it makes sure it doesn't screw anything out. RSS divided by TSS. And you can see right now our fit is 0.106541. Everybody get that?
What was the formula for TSS?
TSS is y, your y, each individual y minus the mean. Square those, and then add those all together. So yi minus y bar, square it, sum those, and that's your TSS value. Okay, did everybody get to that R squared value? You didn't? Okay, let's take a look. Did your other values line up? RSS, that looks good. So now you're gonna do your TSS. Well, you need to create your TSS, you haven't done that yet. And your residual squares, you wanna square those. So it's just equal the square of those. Yeah, just that way we do it the right way and then so now your RSS is just the sum of all those. The sum of the residual square.
Okay, that's where I was messing
Yeah. I don't know why they call it RSS, it's residual sum squared, but it's the sum of the square of the residuals, but they've always done RSS and TSS. It's kind of like the standard. Yep, and that's the right value. So now your TSS is yi minus y bar, so that's your y actual. You need to do the mean of your y first, you haven't done that yet. So you're gonna find the mean of your y, so average, y doesn't do mean, but it doesn't recognize mean, it says. And it's just select your actual y's. That's it. The y actual minus the mean. And make sure you lock. Yeah, you didn't minus sign. There you go. Minus. There you go. And then make sure you lock D19 so it doesn't move. F4. There you go. Now you can drag that down. And now you're going to do a squared column of that one because you need to square it for your TSS. I'd like to do them piecewise like this because it keeps me from making mistakes and having big long equations where I screw them up. So if I do them column-wise, I can see where my mistakes are, I can adjust it. It just gives me that little peace of mind to catch mistakes when I make it.
Your mean y, you get the average of what you're putting in y's?
No, the actual y's.
Your actual y.
Yeah, yeah.
And then the square root of y.
You just sum those up. Yeah, so you just sum those up. It didn't register.
But.
There.
your TSS is your Y, your.
Is your square, your yi minus y bar squared? Yeah, which you haven't calculated yet. So that's gonna be y minus your mean on each one.
I feel like it's mostly memory.
And then make sure you lock that. Make your life easier. You're gonna just lock the B7, not the B14. Because that's gonna move
And
down.
then there's gonna be like one of those override controllers. Yeah, that's, you're gonna have to do in your case, that's not gonna count it.
And then you square those.
So far, I know things change. We have to remember what these.
That's literally me.
And now you sum those for your TSS.
I think
Yep. There you go. Okay, everybody got to that? Okay, so now, for those of you who haven't done your R squared yet, now your R squared just becomes 1 minus RSS over TSS. That's your R squared calculation. That's actually what Excel does on R squared. It just does that. So it's doing all that math behind the scenes, because you can see we haven't given it anything more than what we would give Excel, right? You give it, you're actually giving it your Y's that goes, okay, cool, what do I need? Residuals. Okay, residuals is, you've told me the model looks like this. It's linear, I know the equation looks like that, I know what my Y predicted is. And it's gonna put in a generic number for your slope and your intercept, it's gonna calculate your Y predicted, it's gonna create your residuals. It's gonna square those, that gives you this R, and then it sums those for your RSS. The TSS is like, you gave me Y, I just find the mean, I subtract it from each Y, I do this, where I square them, add them together, TSS, and then it goes, okay, now I'm gonna just start changing the values for my slope and intercept until I get that R squared as good as I can possibly get it. It's literally just a brute force approach, is what it does. It uses some like Gaussian limit or Gaussian reduction techniques. Like, it doesn't matter the techniques it uses, the fact is that's all it's doing. We're gonna utilize that underlying engine it uses to do what it already does, but we're gonna do it with a nonlinear model. Okay, everybody get to the 0.106541? Okay, now I wanna make this value as high as I can. But saying make this value as high as you can is harder to do. We're gonna try it, but we're gonna show 2 different ways and see how it does. So go to your data, go to solver, and now we're going to define information here. And we're gonna say, okay, I want you to change my R squared, which I had already selected, so it might be 11 on mine, whatever it is on yours. And I'm gonna maximize its value, because can my RSS ever become negative? No, because I squared it, right? Can my TSS ever become negative? Right, so what, if I want my R squared to the highest, the 1 is locked. I want this to be as small as possible, and it can't go negative, so what's the smallest value you can get to? 0, right? If it gets to 0, this whole term goes to 1, everybody's happy. So I'm gonna tell it, make this R squared a maximum, and it should be fine, it should solve it fine, because this won't ever go negative, so it's gonna be limited to trying to get to 0. That's its goal. So I'm gonna say, okay, make my R squared a maximum value, and I want you to change these predicted A, B, C's, and D's. These are the things I don't know in my system, right? So I'm gonna tell it, change those. And I can select all of them in one shot like that. And you shouldn't have to change any of the model, the solving method, don't worry about it. They can use GRG nonlinear, don't even know the simplex LP is actually a really simple technique. Evolutionary, don't even know what that one is. But GRG nonlinear is its standard, let it do it. And then hit solve. And it's gonna turn away and just solve your A, B, C, and D and give you an updated value. And it just does it on its own. And I can tell you, once I reopen it, what my actual values were and how it did. Let's see, I want to make sure that this is. And so these are basically the correct answers on it. You'll notice they're off a little at the low end. You can see a little bit of deviation in your data. It means it maybe isn't exactly right, but you have an R-squared of 0.99438. That's pretty good. I would trust this residual as being accurate. It looks a little flatter than I think it should be. So what I'm gonna do is go back into my data and my solver and see if there's something that's, okay, make unconstrained variables non-negative. Should we require A, B, C, or D to be non-negative? We don't really know, right? We have no reason to indicate that it should be non-negative. So we're gonna go ahead and uncheck that and run it again and see what it does. And all of a sudden it nails it. Why? Because it was trying to make sure D never went below 0. And it's like, but we have no reason to force it to not be 0. And right now you're just trying to do a fit. If you had a reason to say, hey, none of those should ever go negative, you could tell it, don't go negative. And let it solve it. And you'll get this, and an R-squared. And so this is literally doing exactly what Excel does. But notice what we weren't required to we weren't required to manipulate our equation and get it to be linear. Once we just define an equation and fit our data, put our data in, we can solve it with any number of variables there and just have it do it.
So you click solver and wait.
You click solver, and then you're gonna, so in solver, it's gonna ask, well, what's your objective? Your objective is your R-squared. So that's the thing you're trying to get to a certain value. So the actual value. And you're gonna say maximum, because we want it to go as high as it can, because it can only go between 0 and 1. Okay? And you're gonna do it by changing your A, B, C, and D. There you go. And you want to say, right now it's constrained to 0. You don't want to, you have no reason to constrain to 0. Okay, and then hit solve. There you go. And it just spits out the answers. This is all Excel's doing with R-squared. It just, the problem is it can't know every possible equation. So it can do this for a small set. Basically, it can do it for linear. If it does polynomial, it's actually doing it for polynomial that it's linearized. If it does it for exponential, it's doing it for exponential that it's linearized. It doesn't know, it knows a very small set of equations and it's doing the work. If you have a complex equation that doesn't look like any of those, you either have to figure out how to linearize it, which is a nightmare sometimes, or you just do this. And you have it solved. And then you say, what are my variables? Well, it's this A, B, C, and D in my equation that I have, and I'm just gonna have it solve this and tell me what my answer is. Does this make sense? Let's do a slightly more complex one. We should have time to do one more. Let's do this guy. So this is one of those where we have some weird sign equation. And I'm gonna insert a bunch of bonus extra lines so I have space to work.
Is this sheet supposed to be on Blackboard?
Yeah, it is. Because people are working with the data.
Oh, there it is. I just like manually typed it in.
Oh, it's like, oh geez. Oh yeah, no, I would never do that to y'all. I'm just putting in bonus spaces so I plan to do everything I want to do. Okay, so I've decided, looking at this is the shape of this equation. Now, would you know this off the top of your head? God no. Once you're doing in multi-dimensions, like x1 and x2, you have no way to know what the shape of this is. So this is where you have to know underlying equations that describe your system. Like this is where you have to get into complex heat transfer, mass transfer, thermo equations and go, oh, this is thermodynamics, it's gonna be this equation. I know it has to look like this, but I don't know exactly what it looks like. So but here I'm gonna give you what this one looks like. So our variables here, doing what we did on the previous one, we're gonna introduce the same idea. So I'm just gonna pull this over here because I'm lazy, and I'm gonna rebuild what I need. So instead of A, B, C, and D, I'm gonna have B1, B2, B3, and I have 4 in this one also. I'm gonna do the mean of my y's. It's gonna look the same as what I did before, so that now I'm gonna make sure it's looking my y's. I recommend keeping, why does this suck so bad? equals sum. There. Nope, not sum, it should be average. There we go. So you guys need my y's. I'm gonna calculate, I'm gonna do the same thing that I did before. I'm gonna need my predicted y. So I'm gonna have to put in my model. My model's a little uglier here. You can see it's, so I'm gonna break it into its two pieces that are added together. So B1 times x2 times the sine of B2 times x1. So that's the first term. And then in that, I'm gonna add, open that up, B3 times x1 times the sine of B4 times x2. Okay. I'll leave that up so that everybody can see real quick. I'm just building that equation at the top with the actual data. And I'm locking my b's, my b1, b2, b3, b4, because those are constants that we're gonna be solving for. And it's gonna be the same for every predicted y. The b1, b2, b3, and b4 are not gonna change. So you real comfortable with what we did there? Anybody not comfortable with what we did there, please tell me. Okay. So we go to the first one. Gonna drag it down. Gonna divide by 0 because there's some stuff it doesn't like. This isn't surprising because, except I didn't lock one of mine. Oops. That's why, make sure you lock all the things you need to lock. So your B4, 5, 6, and 7 should all be locked. I didn't lock my B6 and that threw it off, so let's try this again. There we go, that's better. Now I'm gonna get my residuals of my y's. So it's gonna be y minus y predicted, all the way down. We're gonna need our residual squared. Do that all the way down. I already have my mean of y's, we calculated already, so that's good. So now I can do yi minus y bar. Yi minus y bar, lock the y bar. Yi minus y bar squared.
No, my eyes.
So we're basically just building the exact stuff we did on the last one. That was good. Oh, and if we push those little green arrows there, it just means something doesn't line up for what it saw previously. It doesn't necessarily mean it's a problem. What's happening is this one we locked a value here, and then we didn't here, and so it was confused because we're dragging it down. I'm going to make sure that's what you wanted to do. So it's just kind of alerting you like, hey, inconsistent formula, just so you know. Everything should be fine all the way down. Yeah, good. So now we do our RSS's, which are the sum of my residual squared. We have our TSS's, which is the sum of our yi y bar squared. And our R squared is still right, because it's still 1 minus RSS over TSS. You're gonna notice our R squared is negative. That's because that means that our RSS is much bigger than our TSS. And therefore we're getting a negative value. If anybody's confused, please ask. And now we've got everything we need. We're just gonna do a solver. And we're gonna, oh, yeah, I know, solver. and it wants to know, we want here R squared. We want to maximize it by changing B1, B2, B3, and B4. We're not going to constrain it to non-negative because we have no reason to necessarily constrain it to non-negative. We're going to tell it to solve. It didn't do a great job. We've only gotten to 0.1915. What's the challenge with this one? Why is it struggling?
Your initial guess.
Maybe the negative.
Its initial guess, it's not necessarily the negative, but the initial guess is the issue. This is an oscillating function. It has signs in it. The way it solves is it looks, it takes a step, and it goes, are you good there? Oh, you moved the wrong direction, and tries to move back the other way. So if I'm stuck in one of those, like, part of the curve, it's not necessarily gonna move the whole length and find it. So we have to play with this a little bit and start doing different initial guesses for us. So I'm gonna go ahead and switch my initial guesses to 1 and see how it does. And see, R squared with 1 is actually better than what it solved to. And it's because it was just a bad initial guess, and it's just struggling. And what do you know? With initial guess of 1, it nailed it. I can tell you the values are actually 2.5, 1.3, 3.7, and 0.9. Yes, sir.
So like for the one that we're doing for homework,
Uh-huh.
I mean, I know you don't wanna give us the answer to this, but like, would our unknowns, like our unknowns would be like the B naught, the B1, A, EA, and R?
R is your reaction rate, that's what's here.
Oh, okay.
Yeah. But yeah, otherwise it's B0, B1, A, and EA.
And K, right?
Your K is calculated once you get A and EA. Because R, oh, you're talking about this R, this is your gas constant.
Yeah.
And I recommend using 8.314, because that's joules per mole Kelvin, so it's in an energy term already, and your EA needs to be an energy term. So I just, anytime I'm using a Renes equation, I use 8.314 joules per mole Kelvin, just because I have it. All of these solvers in Excel, and that example we just had where it said, I got a solution, your R squared is 0.14. No, that's a terrible solution. What it's doing is it's doing an iterative guess, and it's almost like, it's not a crapshoot, but imagine you have a data set that goes, I'm gonna pick a value between 0 and 10, it's gonna take your initial guess and throw it in there, it's going, okay, now I'm gonna move 1 this direction, and it goes, okay, I moved 1 this direction, how did you do? Oh, you went up? Okay, then I went the wrong direction, it'll try the other direction. And if it goes up again, it says, okay, I must be near it, and it's gonna start trying to hone in. When you have an oscillating function, that confuses it. Because depending on where you are in the oscillation, it may think you're solving it closely, because if you're at the bottom of an oscillation point, so imagine a curve that's going up exponentially but also oscillates, it's gonna think it's going the wrong direction when it moves away from a certain value when it's not actually there. So that's why the initial guess becomes important. If you ever have it solved and it doesn't look right, give it a new guess and start again. I can promise you I will never give you a problem where the R squared is 0.14. Your R squared is gonna be in the 0.9s, because that's the reality of this data. Now, we're looking at this. What's the one issue with what we just did, and this is before we wrap up today, you don't have to do this one, but if you want to do this one for fun, I can give you the values on it, so you can kind of test your stuff out and see if you're comfortable with it. That is, which was that sheet 2? Your B0 on that one is 55. Your B1 is 5.5. Your B2 is 0.05. And your epsilon is 34.8. So this is a way you can kind of test to see if you know what you're doing, and then we'll do the last one without knowing that information. 34.8 for epsilon. Now, looking at this one, what's the problem with using R squared here? How many independent variables do we have? 2, right? R squared really works for 1. You want to go to adjusted R squared. Adjusted R squared looks a lot like regular R squared, but not exactly. There we go. It looks like this. And it's also, when you see the equation, you're gonna see why adjusted R squared for a single variable looks slightly different than regular R squared. So adjusted, oops, lowercase r squared equals 1 minus, let me make sure I write this right. Yeah, 1 minus n minus 1 over n minus 1 minus p, and then this term is times 1 minus RSS over TSS, which you should recognize that that is regular R squared. N is the number of observations that you're measuring, and P is, I think it's the number of parameters. I want to make sure I use the terminology that's pretty common. So let me verify this before I say it. Is, well, regression variables. So number of regression variables. So looking at this data set we just looked at, what we're dealing with is, let's see. We have 87 observations in this sample, so our n would be 87. We have 2 regression variables. We have x1 and x2. So if we wanted to do adjusted R squared, we would just put those in. And I'm gonna plug values in, but just know you wouldn't have to, you could do it. 1 minus, n1 we said is 87, or n is 87, so 87 minus 1. Our denominator is 87 minus 1 minus 2, because we have 2 parameters.
What are the 2 parameters?
X1 and X2.
Okay.
Yeah. It's basically independent variables. Number. So if you were dealing with a single one, the P would go to 1 if you're just dealing with X1. And then you actually get a slightly different R squared, adjusted R squared than regular R squared for 1. Even though technically you shouldn't, in reality, they are calculated differently, which leads to that. And even in Excel, if you regress it, you look at your R squared and your adjusted R squared, and you're doing just Y versus X, you're going to get slightly different values. Okay, and then this times R squared. Oops, I said I forgot to put an equal sign in. Get rid of that space. Times R squared. So I must have screwed something up here. Oh, times 1 minus the 11. So I have a mistake here. Yeah. So it's actually 1 minus, this is so annoying, 1 minus 1 minus that, which that is R squared right there. So it's 1 minus that. Or you could drop the minus sign and just do R squared over RSS over TSS if you wanted to. But I want to be consistent with how they represent it. 1 minus that. And you can see our R squared is exactly the same. But if we were to adjust this down a little to 2.3, you can see that our R squared is actually slightly higher than our adjusted R squared. So it's compensated for the fact that we have more information than just 1. that make sense? Okay, for class, Wednesday, you'll see a homework, I'll post a place where you can submit your homework. Submit your Excel spreadsheet solving for just, you only have to do sheet 4, you don't have to do or sheet 3, you don't have to do sheet 2. If you wanna do sheet 2, you can just for practice, I recommend it, because I gave you the parameters on that one. So you can try to get to those values.
Do we need to do the adjusted R squared?
If you're doing, yes, if you're doing particularly on sheet 3, because you're solving for 4 different parameters, because you have as input C, D, and temperature, you have 3 input values, you have to use adjusted R squared. They're not gonna be much different because the more data you have, you can see with the more data you have, adjusted R squared approaches regular R squared. Because your n goes up, it swamps the p value. This becomes really important when I have like 30 observations over 20 variables. All of a sudden now it matters. When you're doing 87 observations and you have 2 variables, the difference is what, 86 over 84. Like that, it adjusted a little bit, but not much.
So we have 3 parameters, that's 3 parameters on that.
This one you have 3 parameters, yep, C, D, and temperature. Yep. Does that make sense? This is one of those things that you just kind of have to do. Once you do it once and get your spreadsheet built, you're comfortable doing it. You built the one in class, and bless you, but please build one outside of class on this homework and submit it, because that tool of building it is going to then solidify this in your brain. It always looks the same. It's always, get my residuals squared, or get my y predicted, get my residual squared, get my y minus y bar squared, or y minus y bar squared, RSS, TSS, R squared, adjusted R squared. And if you're doing adjusted R squared, actually have it solve, when you do your solver, have it solve your adjusted R squared to the highest value you can, to the maximum value. Because that's really your target if you know you're gonna be using R squared. Once you do this a couple times, it's just kind of rote practice, and you can build it very quickly. The other reason is, yeah, I can promise you, you're gonna have to do something like this on the exam. You're more than welcome to use a tool you've built. It doesn't bother me for you to do that. Like, so when you're on the exam and I give you data, pull it over into a spreadsheet you've done before. Save yourself some headache of having to rebuild all your equations again. The key is knowing how to apply it, and that's a little more challenging. So if you know how to apply it, then you're perfectly fine doing it. Okay? I'll see you all on Wednesday. Friday, your exam will be proctored by Denise, for those of you who know her, because we have a seminar speaker that's going to be, and undergrads are also invited to it. It'll be over in Scientific 103 from 1 to 2. He's the department chair at the University of Villanova in Philadelphia, doing work on these more sustainable, environmentally friendly concrete developments that we'll be talking about.
So the Friday exam will be something similar to this?
What's that?
So the Friday exam will be something similar to this?
Yep, very similar.
Adjusted.
Oh, you just R squared, so just R squared.